Good morning, everyone, and welcome to the Sampling 2015 workshop. It's great to see so many friends and colleagues in the audience. We hope that you'll enjoy the day here today. So our goal today in the workshop is to expose to you some of the recent activities in our group, in the sample team that you'll see throughout the day, and in the groups of Professor Moti Segev and Professor Oren Cohen from the physics department. And what we'd like to do is to expose some of the activities in Sub-Nyquist sampling and super resolution, and also show you a wide variety of applications to many different areas. So we'll have a session devoted to medical imaging, we'll have a session devoted to communications and radar, and the last session will be devoted to different applications in optical imaging and in optics in general. So that's our first goal here today. Our second goal here today is to further expand our collaborations both within academia and with industry. So we've been very fortunate to work with many good collaborators, as I said, both in academia and in industry, and many of them are here today in the audience. And we're always very excited about furthering our collaborations, looking at new applications. So those of you that may be interested outside, we have little boxes where you can leave your details, and we'd be very interested in following up with you either throughout the workshop or later on offline. Finally, our last goal is to continue and recruit talented researchers to join our activities. So we're very happy to have strong students, both undergraduate students and graduate students, join in our activities. So let me begin by introducing our team. So our team consists of research students. All of them are here today. You're going to see them throughout the talks, chairing the different sessions, giving the different demos. We have master's students, PhD students, and our postdoc, Dr. Leo Reitzman. We also have a fantastic engineering staff. So all of the demos that you're going to see here in the talks today were all developed together with our engineering staff. And again, they're all here today. You'll see them throughout the workshop. Finally, we have an excellent group of undergraduate students who are working with us on our different activities. We have about 20 undergraduate projects in our lab each semester, and these projects are really part of our research and part of our demo developments. The students that work on these projects, they participate in conferences worldwide. They present both the demos and a lot of the theoretical works, and many of these projects are done in collaboration with industry, so this is a very convenient way for us to collaborate with different industries. Finally, I'd like to introduce the optics team, which is larger than what's on this slide, but these are the main people involved in the works that you'll see here today in the third part of the workshop. So these are the groups of Professor Moti Segev and Professor Oren Cohen. Like I said, we've been very fortunate to collaborate with many people worldwide, so I'm not going to go through the various lists. Those of you in the audience, I hope you recognize your names, but I do want to in particular mention three of the labs within the Technion that have been extremely helpful to us. And we wouldn't be able to build our lab without their help. So CPEL, headed by Professor David Malach and Nimrod Peleg, the high-speed digital system labs, and VLSI. Finally, we've been fortunate to work, as I said, with many collaborators in industry. Very partial list is over here, but these are some of the companies who have really been following us from our early development. More recently, we've been working with a variety of medical partners, and this is very important to us because, as you'll see throughout the day, what's very important for us is to move our ideas into technology and into applications. And we're very excited about the medical applications because this is an opportunity to hopefully really make a difference in things that could really matter to people. So we're very excited about these collaborations, and we'll see one of our collaborators from Sheba later on today. And finally, of course, the different funding agencies, so I'm not mentioning all of them, but these are the main ones that besides providing funding for our activities, they also very often introduce us to very interesting problems. Let me say a little bit about the lab itself. So the lab was officially inaugurated in spring 2013. Right now the lab has 4 rooms, so we started with 1 and we're slowly expanding. We don't intend to take over the whole department, so those of you worried, I think we're going to stop here. So right now we have 4 main areas. One area is devoted to the graduate students and to a seminar room where we have all of our brainstorming sessions. Another room is devoted to communications and radar. Another room is devoted to the medical imaging. And finally, we have 1 room of computer space where the undergraduate students could think quietly and further develop the algorithms. As I said, we have about 20 projects each semester. Even though we're a very new lab, we're kind of slowly expanding, and currently we're becoming among the bigger labs in the department. The undergraduate students in our lab have won many awards, and we take great pride in that because as we'll see throughout the day, one of our goals is to kind of mentor undergraduate students to continue to research activities. So the undergraduate students have won Best Demo Awards at ICAST. Actually, we tied against ourselves for first place. on 2 different demos you'll see here today, the Herschel Rich Innovation Award, Kasher Prize, Magnet Award, and many more. Finally, as I said, the undergraduate students actually all take part in the research activities, and this is something that's very important to us. Our graduate students work very closely with them and help mentor them in all different aspects, including writing papers. So many of the undergraduate students are involved in paper writing. Many of our undergraduate students have continued to higher degrees and won the Meyer Award, which is an award in our department given to motivate students to continue to higher degrees. So this is something, again, that's very important to us, even though they continue, of course, to other labs, but it's important for us to train undergraduate students to continue to higher degrees. And as I said, they take part in many demos that we present worldwide at different conferences. So let me just end this part of the introduction by kind of trying to outline the main vision of our group. So we believe very strongly, on the one hand, in developing new theoretical ideas, going into deep theory, but on the other hand, also connecting it with applications. And our hope is to be able to impact both basic science and technology by working closely with collaborators, with industry, and trying to take our ideas all the way from theory into practice. As I mentioned already several times, part of what we believe in is mentoring undergraduate students. So all of the students in our lab take part in research activities. They take part in writing papers. And on the technology side, at least as far as we know, we're the only lab worldwide that actually develops applications of wideband receivers and Sub-Nyquist sampling. So to summarize, we really believe, kind of looking ahead, that in order to have impact, we have to, of course, continue to develop new fundamental theory, but do that by combining it with technology through collaboration with industry, and at the same time creating human capital and basically training the future of future generation of researchers. So let me just briefly describe the agenda of the rest of the day. So after this introduction, I'll begin by giving a very general overview of Sub-Nyquist sampling, so it won't be too detailed, but hopefully we'll give you a general overview. We'll then have 3 parts to the workshop. The first part will be devoted to medical imaging. The second part will be devoted to communications and radar. We'll then have a break. After the break, we're going to move upstairs to room 10 because this room is being used for some other activity. And then we'll start by presenting the lab awards for best projects in our lab. And finally, we'll have the optics and super resolution session that will be headed by Moti and Oren. So let me just point out 2 important things. So first of all, throughout the talks, you're going to hear technical talks and also see live demos. So that's all the equipment you see over here are going to be demos that will be shown throughout the different sessions. And also outside, we have posters that were prepared by our undergraduate students. The posters expand on many of the activities and many of the ideas that you're going to see here, so we encourage you to talk to the students outside and get more details on the posters. So before I wrap up this talk, before I wrap up this part, I want to, of course, start by thanking everyone. So first of all, thank you to my amazing research team, those of you that are here. Pick up your hands so everyone can see who you are. Come on, okay. They're very modest, but this day wouldn't have happened without them, both, of course, because of all the fundamental research results that they developed and because all of their amazing help. So they really put in a lot of sleepless nights in putting this work together. And now I want to mention several people in particular who have really been instrumental both in developing the lab and in putting this day together. And you must come up to the stage for a second. We want to give you a small token of our appreciation. So please cooperate with me. Eli Shushan, who I think is purposely outside so he doesn't have to come up to stage. Kobe, Gloria, could you call Eli for a sec, please? Thank you so much. Ina at the same time. Kobe, come on, someone has to be the first to come up. Kobe. Yoram. Come on. Anat. And Susie, who I know isn't here, part of the talk. And what I want to do now is kind of introduce the main principles of Sub-Nyquist sampling. Like I said, we're going to keep it on a high level, and you'll hear much more of the technical details as we go through the workshop today.
Girl in a digital world.
Okay, so that's to wake up whoever fell asleep meanwhile. So this is a really cool song by Judy Gorman, who's a country singer, and I'm not really sure what she sings about, but this song very nicely captures for us the essence of sampling. Because in sampling, what we care about are analog or continuous time signals, but we know that today more and more of the processing is being done in the digital domain due to the flexibility offered in the digital domain. But of course, if we want to faithfully represent continuous time signals in digital time, we have to have a way to design our A to C, our analog to digital converter, so that we preserve the important information in the signal. Now today, essentially all ADCs in industry are developed based on the well-known Sub-Nyquist theorem that says that you have to sample signals at twice their highest frequencies. And of course, this is a very fundamental theorem and enabled the digital revolution. But in modern application, it has two main drawbacks or two main difficulties. The first is that today, of course, we try to accommodate wider and wider signals, and this means that we have to sample at higher and higher rates. And sampling at high rates means that we have to use very excessive hardware solutions. And this is hard to develop. It consumes a lot of power, it consumes a lot of space. So this is one of the limitations. The other limitation is that even if we somehow manage to sample at these very high rates, we end up with a massive amount of digital data that we have to store, we have to process, and we have to transmit, at least getting it off the machine, so going over the first bus. And this means that at the end of the day, this ADC, that is really the front end in any digital application, is becoming a major bottleneck. So what happens today, right? We have all these cool digital devices, so how do they work? Well, here we have what I call the separation theorem, and this is not a mathematical theorem, but rather a theorem about people. So on the one hand, we have circuit design experts, where their goal is to accommodate wider and wider signals and give us more and more bits, right? They purposely try to give us as many bits as possible. On the other side of the room, and usually behind a very tall brick wall so that there's little communication between these two groups of people, we have the signal processing or machine learning people, and what we do is we get all of this data and we somehow have to process it. Now, typically the first thing we do when we get all of this data is that we actually throw it away. Now, of course, we don't just take it and throw it away, we do it in some smart method, and these smart methods have different names depending on the community you're coming from. So in machine learning, this will be called dimensionality reduction. In signal processing, this might be called feature extraction. But all of these are fancy words to saying we don't actually need all of this data for whatever our task is. Why don't we get rid of it, and then it will be more convenient to process. Okay, but of course, if you look at this from a holistic point of view, what's happening here is that our ADC and our first DSP steps, which are the costly part of the system, this is all being done at the high rate and with high power. On the other hand, when we move to the digital domain, after we've already gotten there, here we start exploiting structure in our signals and we reduce the rate. Now clearly what we would like to do is use the same structure we use in the DSP domain and use it all the way in the front end. So we'd like to have a system that maybe does some pre-processing first, because that will be necessary in order to reduce the rate, but then have our ADC, the first steps, and the DSP all being done at the low rate. This will save us power, it will save us energy, and will save us cost. So this is really the goal of what we're going to be talking about throughout the workshop today. We want to sample only those parts of the signal that are important, only those parts that contain information. And if we can do this, what this will buy us is a variety of different things. So obviously, if we reduce sampling rate, then we're reducing storage, we're reducing power, but there's also other benefits we can get from exploiting the structure. So for example, we can increase resolution, and in fact, the third part of the workshop today, devoted to optical imaging, will talk a lot about increasing resolution. We could increase speed, for example, in imaging, and we'll see a little bit about that in the medical imaging session. We can increase the number of signals we could process. And finally, maybe most interesting, is that we can enable technologies that today are limited by these high rates. So for example, we can enable 3D ultrasound imaging, wireless imaging, which will be a demo we'll see here later today. We could enable cognitive radio, which will be another demo we'll see here today. So the whole idea of what we're going to be talking about is how we could exploit structure already in the analog domain in order to get all of these different benefits. So if we want to achieve this goal, basically we have to revisit some of the main pillars of sampling theory and information theory. So on the theoretical side, we now have to develop new bounds that take the structure into account, both in terms of sampling rate and in terms of information rate, so capacity and rate distortion that takes this subsampling into account. On the hardware side, we have to develop new hardware prototypes that could do this mixed analog digital sampling. And on the application side, we have to demonstrate the ability of these different techniques to reach all of those goals that we've seen in all of these different applications. And each application poses its own challenges and requires its own processing to fit that specific application. So what we're going to do in the rest of the talk this morning is kind of give an overview of the main principles that allow us to exploit the structure. We'll provide a variety of different applications and benefits. I'm only going to touch upon them. You'll see many more details throughout the day. And I'm going to keep it on a very high level. So first of all, it's early in the morning. We know we've made you come out here very early, so we won't burden you with technical details. But those of you who are concerned with all the hand waving that will be going on here, you could find many more of the details in the references. Okay, so here's an outline of the rest of the talk. I'll start by giving motivation, and we'll do that by looking at a variety of different examples where naturally structure exists. We'll then introduce the sampling paradigm, which is basically compression and sampling performed simultaneously. We'll then talk a little bit about what I think is a very interesting and ongoing developing area, which is how we could get Sub-Nyquist sampling even in examples where there is no structure. And then finally, we'll mention a little bit of the applications, and we'll end a few minutes by talking about how we could extend these ideas to nonlinear samples, which is very important, in particular in the context of optics. Okay, so I'm going to start with the motivation, but before that, we can make this interactive. We have enough time. So any questions from the audience? Okay, so I hope that you're still with me. Okay, so let's begin with some motivation. So one of the first examples we looked at is this multiband problem. And in this multiband problem, you have a signal that could be spread over a very wide spectrum, but it consists of several narrow bands. So in reality, most of the spectrum is going to be zero, but the difficulty is that you don't know where these bands are located. Now, of course, any such signal, you could sample at the Nyquist frequency at f max, and clearly you could recover the signal. But this is obviously going to be wasteful because most of the signal spectrum is actually zero. So you're going to be sampling a lot of zeros. But the difficulty here is that if you keep this in the analog domain without doing discretization or anything like that, it's not even clear how you mathematically characterize these types of signals, and then how you use that characterization in order to reduce the rate. Now, one of the reasons that we're interested in this application, of course, it has a lot of applications in defense, but also in the commercial world, there's a lot of interest in this problem because of the field of cognitive radio, and Debbie will be talking much more about that later today. So, in essence, the idea in cognitive radio is that the spectrum is essentially all licensed, right? We know that by looking at our phone bill. But in reality, if we actually look at the usage of spectrum over time, we'll see that in many different time slots, people are not using their allocated spectrum. This is also true if we look in different geographical locations. And this is actually a real plot in Chicago of the spectrum usage over time. So we see that there's many holes, there's many areas that are not being used. Now, these holes are referred to as white spaces in the cognitive radio literature. Now, if we could identify these white spaces and find them over a very wide spectrum, then we could allow secondary users to use the channel. This will, of course, increase the capacity of the channel and, of course, increase the revenue to the cellular companies, which is why they're interested in this application. But this, of course, becomes a wideband sensing problem. So we have a very wideband signal. We have to monitor it continuously without finishing our battery on the iPhone and locate these white spaces to allow secondary users on the channel. So this is exactly the problem that we've seen before. Now, what's interesting about this cognitive radio problem is that actually in this specific context, we don't actually have to recover the signal. All we're interested in knowing is where the signal is located. So in fact, in this case, it's enough, for example, to recover the signal power spectrum. We don't actually have to know the signal itself, since the signal and its power spectrum will have the same location, the same spectral occupancy. Now, this actually raises a very interesting fundamental mathematical question that surprisingly hasn't been looked a lot in sampling theory, and that's the following question. So suppose we have a signal and we want to sample it, but we don't want to sample it in order to recover it. We want to sample it in order to recover its spectrum, or more generally, its statistics. What is the minimal rate that we need in order to recover the signal statistics? And it turns out that actually the minimal rate is very low, and I'm not going to tell you what it is because you're going to have to listen to Debbie's talk, who will be going into the details of minimal sampling rates for estimating covariance. Okay, so let's go back to our general signal structures. So another important problem that appears in many applications is this pulse stream model. And in this example, we have a stream of pulses where what we don't know are the times of arrival and the amplitudes of the pulses. Now, this problem, again, appears in many different applications. It appears in radar, where the different pulses are coming from the different targets. It appears in ultra-wideband communication, where the different pulses are coming from different, so we have different blockers that give us different paths. Besides the direct path, we'll have paths that are coming from different obstacles. And it appears in ultrasound. I'll say more about that in the next slide. So because this problem appears in so many different domains, there's been a lot of work in the signal processing literature in trying to recover these times of arrival and the amplitudes. But all of these techniques require sampling the signal at the Nyquist rate. Now let's think for a minute about what the Nyquist rate is in this particular application. So the Nyquist rate of the received signal, the Nyquist rate of the received signal, because it's a sum of pulses, is just the Nyquist rate of the transmitted pulse. Now the pulse here is the part of the signal that you actually know. You transmitted it. What you don't know are these times of arrival on the amplitudes. So you might be sampling at several gigahertz because that's the bandwidth of pulses that are used today, for example, in radar. But at the end of the day, all you want to find out are these 6 numbers. So clearly here, there's a huge mismatch between the Nyquist rate and the actual degrees of freedom in the signal. But again, we're back to the same question. So then how do mathematically we characterize these signals, and then how do we turn the math into concrete demos and hardware that we can actually show that reduce the sampling rate? So I just want to mention one very important application where this model appears, and this is in the context of ultrasound. So ultrasound is a very popular modality. It's relatively simple, it's radiation-free, and more people are moving towards using ultrasound for medical imaging. And we can think, for our purposes, we could think of ultrasound as very similar to radar. So in ultrasound, we have a known pulse that we send through the ultrasonic probe, and basically what we're viewing are reflections of this pulse as it propagates through the tissue. Okay, so you're going to get something like this. Now the difficulty is that in practice, unfortunately, it doesn't really look like this, otherwise it would be kind of like a standard radar problem. The difficulty is that in the tissue we have many scatterers, and also it's very difficult to send a focused beam. So what we get in practice are distorted signals that don't look like this nice stream of pulses. In order to overcome these obstacles, what is done in practice in ultrasound is that within the probe, we actually have an antenna array, so we have typically between 128 and 256 elements, and we receive the signal in each one of these elements. So basically in each element, you're receiving kind of a time-distorted version of the same signal, where this time distortion is determined by the geometry. So this is something that you know in advance. Now once you have all these many signals, you could go ahead and combine them in a process called beamforming, so it's this nonlinear combination, and Tanya will talk much more about that later today. And once you perform this combination, you're basically both increasing the SNR and increasing the resolution. Now the difficulty though is that you, of course, are not going to do this in the analog domain, right? We don't know how to do this by analog means. So we sample the signal and then do it digitally. But in order to perform these nonlinear distortions, we have to do this on a very fine grid, and this means that we end up sampling at very high rates. So you have to sample each one of the elements at a high rate, and then combine all of the data, which is a massive amount of data, right? We have 256 elements, so it's a massive amount of data. It has to be beamformed to every point in the image. And this creates a huge bottleneck. So it's not really the sampling rate that is the big bottleneck, it's the processing rate that's going to be very huge here. So here we actually have kind of another step that complicates our process. It's not only the sampling rate that we want to reduce, but the question is, if I reduce the sampling rate and now I don't have this fine grid, how am I going to do this nonlinear interpolation once I've reduced the sampling rate? I don't want to go back digitally to the Nyquist grid because then I didn't save anything in terms of processing. So the question is, not only could we sample at a low rate, but could we sample at a low rate so that we could do different types of nonlinear processing on these low rate samples, and that's of course much more difficult. So what we're going to show later today, and Tanya's going to talk a lot about this, is that we could do this by a process we call compressed beamforming. So not only could we reduce sampling, we could actually perform beamforming on these compressed samples. And what this will enable is a variety of interesting things. So we'll see that this kind of paves the way towards high resolution 3D imaging. It allows us to increase the frame rate. And finally, we'll see a very cool demo of wireless ultrasound, which is enabled by the fact that we could reduce the sampling rate. So we talked a little bit about nonlinearities here, and another application where nonlinearities play an important role is in the context of optical imaging. So in fact, in optics, we have two limitations we want to try and overcome. The first is the diffraction limit. So we know that if we try to illuminate an image, then we could only see details that are as large as half the wavelength of the light we're using for illumination. So for example, here, if we're trying to view these nanoholes and we're using green light that's on the order of 500 nanometers, we can only see details up to about 250 nanometers, so we're going to see a blurred image. The other problem is that we only measure the magnitude, not the phase. So in essence, what we're going to be viewing in optics is only the magnitude of the low-pass regime of our signal. Okay, so this is another case where nonlinearities come into account, and here again, we have to kind of see how we could exploit structure in the presence of nonlinear distortions, and the third part of the workshop is going to be devoted to these types of problems. Okay, so that was some innovation. We see that there's many examples where structure is actually prevalent in the signals, and now the question is, how do we get all of these good results, right? So how do we actually exploit that? And to do that, we're going to now introduce the sampling theory, which is actually very simple. So the first part is having a mathematical model, right? We said the difficulty in all of these signals is, first of all, how to characterize them mathematically. And here it turns out that a very simple model is actually quite powerful. So we're going to use what's called a union of subspace model, and this is actually very, very simple. So all this is saying is that what we're going to assume about our signal is that it lies in some low-dimensional subspace, okay? But the subspace is chosen out of possibly infinitely many choices. So we have a huge amount of subspaces that may contain our signal, and at the end of the day, we know that our signal lies in one of them. We just don't know a priori in which one. So basically, we have this mixed estimation detection problem. We have to detect which is the correct subspace, and then we have to recover the signal within the subspace. Okay, so it's a very, very simple model, but let's understand why it's so powerful. So first, let's look at an example. Suppose we have this multiband problem. So recall, in the multiband problem, we know in advance, for example, that we have 3 bands, each one with width b. Okay, this is just an example. Now, if we knew the carrier frequencies, then it would be a simple problem. This is just the lambda rate. So then we know, if we know the carrier frequencies, we could sample the signal at a low rate, which corresponds to the actual band occupancy. Okay, so that means that each one of these guys is a low-dimensional subspace. But in practice, the difficulty is that we don't know the carrier frequencies. So we have many, many options, actually infinitely many, and even an uncountable number of options. We know the signal is in one of them, we just don't know a priori in which one. Now, what's the standard thing to do in signal processing when we have many choices and we don't know the correct one? The standard thing to do is to take linear combinations. And this comes from kind of our subspace thinking, where we start taking linear combinations. Now, if we take linear combinations of all of these options, we're going to get an arbitrary signal from 0 to f max, which means we have to sample it at the Nyquist rate. And that indeed was the standard thinking. On the other hand, if we keep the union model, we're not looking at combinations. We're leaving all of these options. We're just saying we have all of these options, we lie in one of them, we just don't know which one. Now, the reason that this model is so powerful is because it paves the way to this following theorem, which is really the key to Sub-Nyquist sampling. So what this theorem says is that if your signal lies in a union of subspaces, and it doesn't matter how many elements are in this union, the sampling rate that you need is just the rate associated with a sum of 2 subspaces. Okay? So you have maybe 1 million options, and the sampling rate you need corresponds to the rate you would need when you sum only 2 of those options. Not all of the options, only 2 of the options. So what that means in practice, for example, is that in the multiband model, if we have n bands of width b, the minimal rate will be 2nb. In the pulse tree model, if we have L pulses, the minimal rate will be 2L. And notice that these rates have absolutely nothing to do with the Nyquist rate. Okay, the Nyquist rate would be the rate that you need if you looked at the sum of all options. This theorem is saying you only need to look at the sum of 2 options. Okay, so this is really kind of the theorem that allows us to get sub-Nyquist sampling. Now, of course, this is just a lower bound, right? It doesn't really say how we do it. And in order to achieve that lower bound in practice, we actually introduce our sampling framework. So the idea here is very, very simple. It goes as follows. Recall, we have all of these options. We know our signal is in one of them. So the first thing that we do is we take all of these options and we collapse them onto a single low-dimensional space. Okay? And we're going to do this by the process of aliasing, which is something that actually I stood on this stage for many years and taught Introduction to Signal Processing, and we taught how we should avoid aliasing at all costs, right? Never alias your data. So what we're saying here is no, you should intentionally alias your data. Take all of those options and collapse them onto one low-dimensional subspace. Now, once we've collapsed them onto this low-dimensional subspace, we could go ahead and sample it at a low rate, right? Because a low-dimensional subspace corresponds to a low sampling rate. And this could be done using a standard ADC. So this is very important to us. We want our framework to be practical. We want to be able to show you all of these demos. So we don't want to have to develop these crazy new ADCs that people are not going to use in practice. So we use standard ADCs after we've done this pre-processing to collapse the data. Now, of course, after we've done all this in the digital domain, we now have to figure out, we still have our detection problem, right? We have to figure out from this collapse of subspaces which was the correct subspace. And this we're going to do in the digital domain. So this is good because the detection we could already do digitally. And we're going to do that by using the recent ideas of compressed sensing. Okay, so we'll talk more about that later on in the talk. So the overall flow that we have is as follows. We have our signal. We pre-process it by analog means. This is what's going to do the aliasing. We then acquire the signal with a low-rate ADC. And finally, in the digital domain, we use standard techniques like compressed sensing or different subspace identification methods in order to recover our signal. Okay, now of course we have to explain each one of these blocks. So let's start by explaining this analog pre-processing, how we actually do it, and why we need it. Why can't we just go ahead and sample our data at a low rate? So this is a very simple illustration to show you why this is needed. Let's look at this pulse tree model. We have 2 pulses. So our theory says that we need 4 samples. But now if I just go ahead and take 4 samples at a low rate, most of my samples are actually going to be 0. So I'm not sampling the energy in the signal. The same thing, of course, is true in the multiband model. So if I have several bands, n bands of width b, if I only sample certain areas of the spectrum, with high probability I'm going to be missing my signal. So it's not going to give me the required information. Therefore, what we do instead is we introduce this aliasing. So we take these pulses, we smear them. So here we're doing aliasing in time. We smear them, and this could be done very conveniently by using, for example, an appropriate analog filter. We'll talk more about the filter later on, but intuitively we could see that we could get the smearing by filtering. And now if we go ahead and take the same 4 samples we took before, these samples are now going to convey all of the information in the signal. Okay, now of course, this is the good news. So the good news is that these samples are no longer 0. They contain the energy of the signal. The bad news, of course, is that it looks like we lost resolution. So now, when I have a sample over here, it has a contribution from this pulse. Well, if I have a sample over here, it has a contribution from this pulse and from this pulse. So it's not clear how we could localize our pulse. But like we said, that we're going to be doing in the digital domain, and we'll talk more about that shortly. The same thing is true in the multiband problem. So here we're going to do aliasing in frequency. So we're going to take all of our signal, regardless of where it resides, we're going to make sure that we alias it all down to baseband. Now, once it's all in baseband, we could sample it at a low rate. We get all of the energy of the signal, and then we could go ahead and recover it by digital means, just as before. Okay, so what are these digital means? Well, on the high level, you could think about this just as subspace recovery, right? We had many subspaces. We're viewing kind of a sum of all of these subspaces, and now we have to identify the correct one. This is kind of a standard problem in array processing. So we could use array processing techniques to recover the subspace. The more modern way of viewing these problems is within the theory of compressed sensing, but actually there's a nice analogy between compressed sensing and subspace methods. So it's really kind of different ways of attacking the same problem. What's also nice is that we could extend these ideas to nonlinear sampling, and like I said, this will be important in the context of optics. So we could extend compressed sensing to deal with nonlinearities, and therefore we could, all of the ideas I'm showing today could work even when we have nonlinear samples, for example, in phase retrieval problems. So let me just give a very extremely compressed version of compressed sensing. So I'm not going to go into the details, but those of you not aware of this growing field, I do encourage you to take a closer look at it. So the idea in compressed sensing is that we're trying to find a very long vector x, so it could be very long, but we know that it's sparse, meaning that most of its elements are actually 0. It has only a very small number of non-zero elements. And what compressed sensing says is that if I have a long vector with, let's say, k non-zero elements, then I could recover it from on the order of 2k measurements, okay, which is much smaller than the length of the vector. And I could do that as long as my sensing matrix, okay, this matrix that multiplies the vector, has nice properties. So I'm not going to go into the technical details, but essentially that matrix has to look like a random matrix. Now, in practice, if I want to be able to recover x using computationally efficient algorithms and in a way that is robust to noise, then we know that we need on the order of k log n measurements in order to recover the signal. Okay, but that's much smaller than n. So usually if you have a vector of length n, you need n good measurements in order to recover it. What this is saying is that if it's k sparse, if it has only k non-zero values or k dominant values, then all you need is on the order of k log n measurements in order to recover it. Okay, now this is a very, very powerful theory, but of course it's a digital theory, so it can't be applied directly to our continuous time analog signals. But the way we use it in our context is slightly different. So in our case, this vector x basically represents the different subspaces. Remember, we had many subspaces. Those were our options. We collapsed the subspaces by our hardware. So this measurement matrix phi is now describing the hardware that collapses the subspaces. And basically our problem now is to locate the correct subspace, which is basically identical to locating the support of the non-zero values. Okay, so again, without going into the technical details, you see the analogy with compressed sensing, and therefore we could use compressed sensing techniques adapted to fit our context, but we could use the basic techniques from compressed sensing in order to recover after we've sampled by analog means. So we sample using analog tools, we don't sample using compressed sensing, but in the digital domain, we're going to use ideas of compressed sensing in order to recover the signal or the correct subspace. Okay, so that's really kind of the main idea in a nutshell. Now, one thing that we didn't talk a lot about is that we said, okay, we need aliasing, and we kind of, said we could, roughly speaking, get it by filtering in some sense. But the question is there some optimal way to design this aliasing? So clearly, we highlighted the benefits of aliasing, but of course there's disadvantages to aliasing, and the main one is the behavior in the presence of noise. So aliasing is going to enhance our noise. And therefore, it's very important to design this aliasing in a way that we don't introduce too much noise into the system. So one approach we could take to designing this aliasing is to say, okay, why don't we set up this problem as an estimation problem under a certain sampling rate, and ask ourselves what is the best sampling mechanism to use so that when we recover the signal, we'll minimize the mean squared error in the recovery process. Okay, now of course this is a very difficult problem, so we can't look at the MSC directly, but we could look at bounds on the MSC and try to optimize the bounds. Now a standard approach when we talk about bounds is to look at Cramér-Rao bounds, but actually it turned out to be quite difficult, and that's because Cramér-Rao bounds typically deal with finite length vectors, when we try to estimate a certain finite number of parameters. Here we're trying to estimate a continuous time analog signal. So it's harder to think about deriving Cramér-Rao bounds, but nonetheless, I won't go through the details. We could actually get compact expressions for the Cramér-Rao bounds in this analog setting, and the actual expression doesn't matter, so I'm not going to go through it. What's important is what is the sampling mechanism that optimizes this bound. And it turns out that that actually has a simple solution under general conditions where all of the examples we've seen so far actually satisfy those conditions. So what we see in this case is that the optimal sampling mechanism is simply to use sinusoids. Okay, so if you sample with sinusoids, you're guaranteed to minimize your mean squared error. Okay, so that's the good news. Of course, the not so good news is that sampling with sinusoids is easy if we have a small number of them, but if I need 20 samples and I need 20 sinusoids, then from a hardware perspective, it's not so easy to put all of these sinusoids on the same board, have them synchronized, etc. But here, Fourier analysis comes to our rescue. So we know, for example, that any periodic signal, and it could be any signal, it doesn't matter what it looks like as long as it's periodic, we know that a periodic signal can be written as actually an infinite sum of exponents. So now, instead of having to multiply with many sinusoids, all we have to do is take our signal, multiply it by one single periodic function. That gives us all the sinusoids we want. We could then go ahead and filter the signal to get rid of the carriers that we don't need and maybe shape the different tones, and then we could go ahead and sample at a low rate. Okay, so here I'm plotting several branches. In fact, all of this could be done in a single branch. There's different trade-offs in terms of rate and hardware. I won't go into them here, but conceptually we could do this all in a single branch. Okay, so all of the prototypes that you see over here, these are all of the different sampling mechanisms that were developed in our lab, and actually they're all sitting here in front of you, so you'll see them later on throughout the demos today. All of these were based on this very simple principle, and like we've shown, we know that this is going to give us something that is optimal in a mean squared error sense. Now what's nice is that it's not only optimal in a mean squared error sense, so those of you who are fond of communications and information theory, we can show that the same mechanism that we just introduced is actually optimal also from a capacity perspective. So instead of thinking of our problem as a sampling problem, we can actually think of our problem as a capacity problem or a communication problem, where we have a signal and the structure, where we have a channel, sorry, and the structure of the signal is captured by the structure of this channel. And what we want to do is send bits over this channel, where at the outcome we're going to subsample the channel and try to recover our bits. And we can now ask ourselves, what is the optimal sampling mechanism that will maximize the capacity over this type of channel? And it turns out that the same exact architecture we've seen before is actually optimal from a capacity perspective. So this was joint work done with a group of Professor Andrea Goldsmith from Stanford, and we're working a lot on this interface between information theory and sampling theory. So we won't see a lot about that here today, because today really is devoted much more to applications, but on the theoretical side, there's a lot of interesting questions here on this interface. So just to describe the problem maybe a little bit better, but not going into too much detail, so how do we think of the sampling problem as a communication problem? Let's look again at the multiband problem, which is easy to kind of explain. So in the multiband case, we could think of the problem as follows. Suppose we have a channel, and we know that what this channel does is that it passes certain bands of information, but we don't know in advance which bands it's actually going to allow. Okay, so in this way, we kind of capture the structure that we've seen in the sampling problem. Now what we want to do is design a sampler that's blind, so it doesn't know the channel realization. We want to design a sampler that will maximize the capacity for every possible realization. Okay, now of course we can't do this, right? We can't maximize the capacity for each realization because we don't know the realization. So instead we could try a min-max approach where we look at the loss we get with respect to a sampler who knew the correct channel, and we try to minimize the worst case loss with respect to the optimal capacity. So it turns out that, at least asymptotically, we could actually derive an expression for the minimax capacity loss, and then we could go ahead and optimize it and get the optimal sampler. So I'm skipping through all the details, they're quite involved, but at the end of the day, the optimal sampler is exactly the same sampler we've seen before. So we multiply with these periodic functions, we low pass and sample at a low rate, and in fact, what comes out from the theory here is that these periodic functions should have Fourier coefficients that are random. So this is actually quite nice because those of you familiar with compressed sensing, we know that random always comes into play in compressed sensing, and this kind of gives us a different viewpoint of where the random comes into play. So also in terms of capacity, using random sequences is in fact going to be optimal. Okay, so that kind of covers the fundamental theory. Again, like I promised you, I didn't go through the details. Of course, there's many more details here. Those of you interested, I'm available. I'll be happy to talk about it during the day. And of course, you could go ahead and look at the references. So I want to take just a few minutes now and talk a little bit about how we could reduce sampling rate without structure. And this, of course, seems puzzling, right? Because if we don't have structure, how could we reduce the rate? Well, of course, that's because we're interested in different problems, not actually in recovering the signal. So two examples, and there's many more, but two examples that I want to mention where we could reduce rate without structure is one of them we already mentioned, it's covariance estimation, and Debbie will be talking more about that, so I won't spoil her talk. We'll skip that one. The other one, again, done together with Professor Andrea Goldsmith and her student Alon, is when we take quantization into account. So until now, we only talked about sampling. We didn't talk about quantizing the data. Now, of course, when you quantize the data, you're introducing distortion. And the question is, if you're going to be introducing distortion anyway, maybe we don't need the optimal sampling rate. Maybe it's okay to have some distortion from the sampling rate, but it will be compensated by having less distortion from the quantization such that altogether we end up with the same distortion. And this actually turns out to be true. So just to put things in context, mathematically, when we talk about sampling theory, typically we're only concerned with going from continuous time to discrete time. Typically in sampling theory, we don't actually take the quantization into account, right? So think of the famous Shannon-Nyquist theorem. It doesn't say anything about quantization in the simple version of the theorem. On the other hand, typically when we talk about source coding or Shannon theory, we're talking about taking a signal that's already discrete in time and making it discrete in amplitude. Okay, but really what we want to do is merge these two. We basically want to develop rate distortion theory for continuous time signals when we take both the sampling and the quantization into account. So again, of course, this is an oversimplification. Again, I'm not going through the details, but if we think about this again from an oversimplified point of view, in standard rate distortion theory, what we're interested in is designing an encoder-decoder pair at a specific bit rate R that will minimize the distortion between the recovery y hat and the input y when we typically assume that both of these are discrete in time. On the other hand, in our problem, we have a continuous time input. Okay, we're going to sample it, we're going to encode it, so we have two parameters here, the sampling rate and the bit rate, and then we have the recovery, and what we want is actually to minimize the distortion between x hat and x, the analog distortion. And here the sampling rate is basically a parameter, so we could get different distortions at different sampling rates, and really what we want is to look at what is the minimal sampling rate that will give us the minimal distortion. So we're optimizing also not only over the encoder-decoder pair, but also over the sampling function. Okay, so now again, I'm not going to go through the technical details. Let me just kind of highlight the end results. So first we could develop expressions for the rate distortion curves of these continuous time problems for a fixed sampling rate. So for a fixed sampling rate, again, I'm not going to go through the expressions, but we can show that the distortion function actually very conveniently can be broken into two terms, one that has to do with the sampling function and one that has to do with the actual quantization. Now, once we have these general rate distortion curves for these analog signals, we could go ahead and try to optimize them over all sampling rates. And what we'll find is, very interestingly, that actually the minimal rate is almost always below the Nyquist rate. So we could get the optimal rate distortion by sampling at much lower rates without losing anything. And again, the important thing here is that we didn't really assume anything about our input. Okay, so for example, what I'm showing here are several examples. What we can show more specifically is that as long as the power spectrum density of the input signal is non-flat, okay, in the flat case, this black case, we don't gain, but as long as it's not flat, the sampling rate we need to achieve the minimal distortion is always lower than the Nyquist rate. And here what I'm plotting is the optimal sampling rate, the minimal sampling rate that is needed as a function of the number of bits. The red and the blue have the same bandwidth as the black, but of course they're non-flat. And you see that the sampling rate is always lower than the Nyquist rate, which is in this case 1. Of course, we don't need our signal to be band limited, so we could determine the optimal sampling rate even for signals that are not band limited, like this green curve over here. Okay, so we don't need the same constraints we need in Shannon-Nyquist theory. So this is very nice because it allows us to extend rate distortion to general inputs, even non-band limited inputs, and it actually tells us that when you take quantization into account, you might not have to sample at such low rates, at such high rates as you need when you don't take this quantization into account. And of course, in practice, we always quantize our signal. So this is something nice to think about moving ahead in terms of practical applications. Okay, so this kind of wraps up the theory. We have a few minutes left. And what I want to do in the next few minutes is I'm not going to go through any of the details because all of the applications you're going to see throughout the day, but I just want to touch upon them briefly. So this is kind of a preview of what you're going to see later. And hopefully we'll convince you by the end of the day that despite Albert Einstein's famous quote, actually the ideas that we've showed you now do translate into practice. So I hope you're convinced by that by the end of the day. Okay, so here are some of the examples we're going to see later today. So for the cognitive radio problem, we're going to use, I already explained this basic idea. Debbie and Shachar are going to explain it in much more detail later today. So this is what we call the modulated wideband converter, which was designed for the cognitive radio problem. What it allows you to do is to sample a very wideband signal at very low rates. Like I said, you could use multiple channels. You could collapse this down to a signal channel. So again, we'll hear more about the theory later on today. Here is the demo that Shachar is going to show us. So what you see over here is the actual board that Shachar and the engineers developed in the lab. And what this board does is it samples at 6% of the Nyquist rate. And you'll see a demo here, for those of you who don't believe, it actually recovers in real time, even from this very low sampling rate. So this demo won first place at ICAST last year. So hopefully you'll enjoy it as well. And we'll also hear some extensions about it later today. So besides the live demo, Debbie's going to talk a lot about how we could actually make this robust to noise. And this isn't only a kind of practical problem. There's nice new theory that could be developed in order to make the MWC more robust. We'll talk about how we could use the MWC to actually recover direction of arrival. And this is a nice example of the undergraduate students who take part of our research activities. So the DOA estimation problem was actually developed. Debbie supervised the team, but the undergraduate students were actually the ones who developed it. You'll actually hear them later today because they're receiving an award, and they'll give a talk about this DOA estimation. And finally, we'll also see how we could use this cognitive radio idea in a distributed fashion, which is very important when we have, for example, shadowing and fading. And then if we can combine information from multiple users, we can actually get much better recovery. So Debbie and Shachar are going to talk more about that and show you a collaborative demo as well. Okay, so that was the multiband problem. In terms of the pulse stream problem, here we've already showed by the theory that in order to recover a stream of pulses, we need 2 L samples, and in fact, all we need are 2 L Fourier coefficients. Okay, now in theory, we could use any 2 L Fourier coefficients. To achieve them, like I said already, but here we have a little bit more detail, we take our signal, we're going to filter it, and all we need is that this filter satisfies these mathematical conditions. So I'm not going through them, but they're quite easy to satisfy. For example, this is a filter that we call the sum of sinks filter that actually satisfies these conditions, and it could satisfy them for any desired set of Fourier coefficients. It's a very simple, compactly supported filter, so it's easy to do in practice. We then sample at a low rate at the output, perform an FFT, and the coefficients that we get are exactly those desired 2 L Fourier coefficients. Okay, so the boards you're going to see today, for example, for the radar demo, are actually built on this principle. Okay, so the only question left is how we actually choose those Fourier coefficients. So we said that we could use any 2 L Fourier coefficients. Again, I'm not going through the theory. All of this could be made rigorous, but intuitively, there's 2 different constraints here that we want to satisfy. On the one hand, we want to spread out those coefficients so that we have a wide aperture. Wide aperture translates to good resolution. We know that from array processing. On the other hand, we need at least 2 frequencies to be close to each other. Otherwise, we're going to have ambiguities. okay, which is a bad thing. So what we do is a very intuitive compromise. What we're going to do is we're going to use several bands. So because they're bands, we have close frequencies within the band, but these bands are going to be spread out randomly over a wide aperture. Okay, so this kind of gives us a compromise between these two constraints, and of course, again, we could prove rigorously that this will give us a good compressed sensing matrix at the end. So this is the prototype build based on this principle, and again, you're going to see it later today in the context of radar. So like I said, one of the main applications here is radar. And radar, of course, radar is a wide field. There's a variety of different applications in this context. So one is in pulse Doppler radar, where we know that if we want to get good resolution, we have to use very wide band signals. And this, of course, entails high sampling rates. Another is in spatial radar. So if we think about MIMO radar, where we have multiple antennas, again, here we have a spatial Nyquist theorem. So we have to spread them out spatially and half the wavelength. And this means that if we want to get a wide aperture, we have many, many antennas. So what we're going to see in the talks later today is, first of all, that we can use these ideas to reduce sampling and processing rates in the context of pulse Doppler radar. So Omer Bar-Ilan, who graduated from our group and is working in Rafael, will talk more about that. Debbie will talk about a very interesting application where we get a different benefit from this low rate sampling. So instead of looking at this as low rate sampling, we could look at the time it takes in order to get the samples we need to recover the targets. And this is very important in radar. So we could get what we called reduced time and target radar, where for the same time that you would typically need in order to identify a target's velocity, we could actually identify several targets. Okay, so this is very important in the context in different defense applications. We'll also talk about cognitive radar. So using these ideas, we'll see that actually we could get good detection using a radar signal that is non-conventional. So instead of having a signal that takes a wide bandwidth, we can actually transmit a signal that consists of several narrow bands. And the advantage is that this allows us to have a cognitive system where the radar coexists with communication channels. So we can imagine a system where we have communication channels, right? We use our cognitive radio to identify which bands are being occupied. And in the bands that are not occupied, we can now coexist with the radar. We could send a radar signal. And typically this can't be done because you need a wide band. But what we're going to show is that we could get the same resolution and the same detection accuracy when we don't need to transmit a wide band. We only need to transmit several narrow bands that don't have to be consecutive. Okay, so this will enable cognitive radar, and we're going to see a demo. One of the demos here will show that later today. Debbie's going to talk a little bit about David's work, where we could extend these ideas to MIMO, so we could reduce rate spatially. And in the context of MIMO, this means that we could develop a radar that has both a small number of antennas and a small number of samples. And finally, more work that we simply don't have time today, so we'll have to leave this for our next workshop. We could use these same ideas to resolve range ambiguity instead of using kind of staggered PRF ideas. And Kfir is developing methods that actually take these ideas and the ideas of ultrasound and combines them in order to get high resolution, low sampling rate SAR. Okay, so this is the actual prototype developed by Dan and Robert will be presenting the demo later today. This demo also came first place, so this was a funny story because it was anonymous, so when you actually, the competitions were submitted, you didn't know which groups were coming from, and then they announced that they were two different demos that they couldn't decide between, so they're giving the first prize to both demos, and both of the demos were from our group, so both the radar and the cognitive radio won first prize. And the reason I take so much pride in this is because here you see the undergraduate students over here. Shachar is now a graduate student in our group, but he was an undergraduate student when he developed and presented this. So this was all done by undergraduate students in our lab. Okay, finally, the last application we're going to see, which is actually going to be the first one you're going to see in the session right after I finish talking, is the ultrasound imaging. So I'm not going to spoil the effect. Let me just show you the final images. So here you see a standard image, and all of this data is actually coming from a true GE ultrasound machine. So we, of course, are very grateful to our GE partners who have worked with us hand in hand in developing these results. And the ultrasound machine, you'll see it later today. So here you see a standard image. Here you see, this is cardiac, by the way, in case you're wondering. It looks like a baby, but it's not. Here you see the same image sampled at 1/10th of the Nyquist rate, and here you see the image at 1/32 of the Nyquist rate. And although this image already starts to look a little bit distorted, clinically it actually contains the same value. And we happen to have with us today a cardiologist who you will later meet, and he will describe what he sees in these different images. Okay, so Tanya and Alon will be talking much more about the ultrasound later on in the session today. We'll also see a demo of a wireless ultrasound. So because we could reduce the rate, we can actually now enable wireless ultrasound where we send the data, because it's at a very low rate, we could send it over a very simple wireless device, a standard wireless device you could buy for a few shekels or a few tens of shekels. We could send it to the cloud or to the other side of the room or the other side of the hospital and recover the image remotely. So we'll see a demo of that later on today as well. Okay, so I have about 2 minutes left, so let me, in a very compressed version, talk a little bit about how we expand these ideas to nonlinearities. So until now, we talked about applications where our measurements were all linear, but we've mentioned already that, for example, in the context of optics, looking at nonlinearities is very important. So I won't go into this in too much detail. We also don't have time, and also Moti and Oran, who are the experts, will be talking about this much more later on today. So just to convince you, okay, that actually the phase is important, we could take this very, very simple experiment, because the first thing people tend to do is to say, all right, let's just ignore the nonlinearities and recover as if we were recovering from linear measurements. But that actually doesn't work. So this is a standard example anyone could do in a MATLAB. Don't do it with real cats and dogs, but you could do this on MATLAB. So if you take these two images and you compute their Fourier transform, you keep their magnitude, but you swap their phase. So you give the cat the phase of the dog, and the dog the phase of the cat, and now you just apply a standard inverse Fourier transform. So, okay, I think you could guess already what's going to happen. Your cat is going to turn into a dog, and your dog is going to turn into a cat. Okay, so this just illustrates that phase is in fact very important. We can't simply ignore it. Now, mathematically, that's actually quite upsetting, because it's difficult mathematically to take the phase into account, but from a practical perspective, this is very important. So again, the third part of the workshop is going to be devoted to these types of applications, but very briefly, 2 of the applications that we've looked at quite a bit are measuring of ultra short pulses. And the reason here that we get a phase retrieval problem is that if we want to measure a very, very short pulse, then we have to measure it by using another short pulse, and typically we just measure it by convolving or correlating it with itself. Now, of course, if you look at the correlation of a signal with itself, then in the Fourier domain, you're actually getting the magnitude of the Fourier transform. So that turns into a phase retrieval problem. Another important problem is coherent diffractive imaging or lensless imaging, where we use X-ray because they have very short wavelengths, so they could give us good resolution. But in this case, we don't have lenses, so what we're going to view is only the diffraction pattern, which again, of course, is just the magnitude of the Fourier transform. So these are some of the examples, and again, we'll hear much more about that later on today. Now, like I said, mathematically, the phase retrieval problem is actually very difficult. So again, I don't have time to go through all the technical details, but in a nutshell, what we know is that we cannot guarantee a stable solution by any known algorithm for the standard phase retrieval problem. So what do people tend to do? Because we do want to get some sort of mathematical analysis that sheds some light into the problem. So our standard, a more recent trend in the past 10 years or so, is to look at what we call random magnitude measurements. So we look at the magnitude of the inner product between our unknown vector x, or unknown image x, and a set of random vectors. Okay, now this is not necessarily what happens in practice, although we could create scenarios where this is close to what happens, but at least it will give us some insight into the problem. And once we look at this random problem, what we could prove, for example, and this is recent work that was done together with Shachar Mendelssohn here at the math department. So for example, we could prove, if we have these random measurements, that if we're trying to recover a vector of length n, then actually we only need n log n measurements in order to guarantee a unique stable solution. And if the vector is k-sparse, then we could find a unique stable solution from k log n measurements. Okay, now those of you that are keeping track, the k log n was the same factor we got in the linear case. Okay, so that's quite surprising that actually the same number of measurements we need to solve a linear problem is the same that we need to solve this nonlinear problem. Okay, now of course the caveat is that it's not really clear how we solve this problem. So this is just a theorem saying it's enough to have k log n measurements for stable recovery, but of course the difficulty is that to find this stable recovery, we have to solve this non-convex problem. So it's not so clear how we do it in practice. So again, without going too much into the technical details, we've worked on this problem separately. So this is work done together with Amir Beck from industrial engineering, who's of course an optimization expert. And we've looked more generally at solving different non-convex, non-linear problems subject to sparsity constraints. And for these types of problems, we've been able to develop necessary optimality conditions and develop algorithms that achieve these conditions. So more specifically, those of you familiar with compressed sensing, 2 of the kind of leading greedy algorithms in compressed sensing are iterative Hard thresholding and orthogonal matching pursuit. So both of these algorithms we can actually extend to the nonlinear setting and prove that they converge to these necessary optimality conditions. Okay, so I'm not going to go through the details, but I do want to mention guess bar. So if we take these general algorithms and specify them to the phase retrieval problem, then the extension of OMP results in this algorithm that we call guess bar, and it was developed together with Yoav Shechtman, who was Moti student and is now doing a postdoc at Stanford. And the reason I mention guess bar is because you're going to see it a lot later on in the optics session. So this is actually the algorithm that we're going to use in most of the optical applications. Okay, so just one more note before we wrap up. We said that standard phase retrieval problems we'll look at Fourier measurements are actually fundamentally hard, right? It's not that we just don't know how to analyze them. They actually are hard. There really is no unique stable solution in general. But what we can do in order to make these problems nicer is that we can introduce redundancy into our Fourier transforms. And there's various ways of doing that. I don't have time to go into that. But one interesting way, again, that we're going to see later on today is by using short-time Fourier transforms. And this is done in optics for many, many years. They just didn't view it in this form. Okay, but what's nice about short-time Fourier measurements is that because we have redundancy, since we use a window that, of course, is an overlapping window, we can actually prove, and these are very recent results, we could actually prove mathematically that even without sparsity, for almost all signals, we could actually recover it in a stable fashion from these short-time Fourier measurements. So this really kind of paves the way to practical ideas where we design the measurement system to take short-time Fourier measurements rather than just Fourier measurements, and we'll see an example of that later today in the optics session. Okay, so these are some of the optical examples. In the interest of time, I'm going to skip them. Hopefully you'll be curious enough to stay till the end of the day and see these actual applications. Okay, so let me wrap up. It was a very high-level talk, so we didn't go through the technical details, but hopefully it gave you an overview of what we can do with these Sub-Nyquist ideas. We've talked about how we could use these ideas in practice, also in theory, but also in practice. And again, these different demos should convince you that these ideas actually work in practice. We've highlighted some of the interesting fundamental theoretical questions here. There's many more questions that we didn't have time to go into, but hopefully some of you will be encouraged to join our efforts. There's very interesting problems here on the optimization side, on the information theory side, on the hardware side. But really the important thing, the take-home message, is that we could exploit structure in the analog domain. This leads to a variety of both interesting fundamental theoretical questions and a lot of very interesting practical questions. So those of you that kind of want to see more details, you're encouraged to go ahead and look at our website. We have a website dedicated to this. We have a recent book on compressed sensing where there's more details on the digital side, and a recent book on sampling theory where there's also more details on the analog side. We have a lab webpage where you could see much more about the activities of the lab, and thank you very much for your attention.